Hello and welcome back to Discrete Mathematics. This week we're going to be looking at graphs. Graphs are kind of going to start a new sort of section of chapters here where we're going to talk about sort of the relationships between things. So far we've been doing a lot of the predicate logic where it's been very straightforward, but a lot of things are sort of defined in terms of other things, whether that's forces in economics with supply and demand. Price of a commodity may depend on how much of it is available. Manufacturing processes are often dependent on other steps. All those sorts of things are defined by their relationship to other things. So we want to find a way to define that mathematically, to create a language that we can use so that we can explore the relationships between things with the same sort of precision that we would do with any other sort of math. And so that's why we get to our first of these types of subjects, which is graphs. So graphs are basically a way of showing the relationships between two objects. If you had to, sketch out something, let's say a process. Silicon Valley, obviously, whiteboards are integral to the process. I often say that to become a computer programmer, being a computer programmer is not about what you do on the keyboard, it's about what you do on the whiteboard. And what you see are a lot of graphs. Here's a step in the process. Then there's a transition to this step in the process, but you could also branch out into this step of the process, right? They draw these graphs just to try to understand the problem. What do those transitions look like? What work needs to be done with those? What are the different states that we arrive at, in these different processes? A lot of this stuff can be defined with a graph. And so we are going to look at some definitions, some basic ways that we can use them. We'll actually look at a very famous problem that helped start graph theory. So there we go, graphs. Graphs basically are created from edges and vertices. Now I will say that a lot of books will say edges and nodes. I personally heard nodes in college, but they mean the exact same thing. Edges and vertices, basically you get a diagram of whatever it's going to be, dots, circles, squares, your things, right? They represent the things in your relationships. And then you connect them, and we're going to call those vertices or nodes, and you're going to connect them with edges. Those edges could be lines, curves, whatever, but those are going to be our relationships. Sometimes those lines can have arrows on them because the relationship is directional, right? Maybe it's a one-way street. So if it's a one-way street, well, I can go from point A to point B, but I can't go from point B back to point A because it's a one-way street. I'm going to have to go to point C, D, and then back to A, right? That's just the way one-way streets work. And so if the relationship is directional, we might draw an arrow on it. That would mean that our graph is called a directed graph. But for any directed graph, there's sort of an underlying undirected graph, which just shows that there is a connection somewhere between B and A, going one direction or the other. An undirected graph might also just be, hey, these things are connected, but there is no direction. You can go either way with this sort of a connection. Again, we're talking very vague. So we're talking about objects and the relationships between objects, or even ideas and the relationship between ideas. Your mileage is going to vary as to whether or not what these things represent, right? But vertices, edges, if edges have arrows, it's a directed graph. If it doesn't have arrows, undirected graph. Now, the other thing to note is that we are not trying to draw a picture of a system, right? You can draw a graph of, let's say, a city grid in downtown Fresno without actually having to get the lengths of the streets right and everything, or even the locations of the intersections. You're not trying to draw it to scale or anything. You're just trying to draw the connections between the two. The only thing that matters is that you've got, your objects, and you've got the relationships between those objects, the vertices and the edges. It doesn't matter actually how you draw them. What matters is, are they connected or are they not connected? So here we're going to have a very famous example. Here is the city of Königsberg. I'm probably mispronouncing that, but then again, I remember having a friend bring over their other friends from Sweden, and their son was named Jon, and I said it was Jon, and they said, no, it's Jon, and I said, Jon, And they said, no, it's Jan, and I don't think I can pronounce anything in Scandinavia, or in this case, Russia. But point being, Königsberg, however you pronounce it, was a city that was sort of bisected by this river. And so there were 4 different areas of the city. And the 4 different land masses were connected by bridges, as you can see here in the drawing. The idea was that in the city of Königsberg, it kind of became a problem. Can you cross all of the bridges only once? Can you see every bridge, cross every bridge, but only have to cross the bridges once if you're visiting the city? And so that became the question. Can you cross every bridge in Königsberg exactly once? Yeah. So you have to cross every bridge, and you can't cross a bridge twice. Now, you could try to do this right now in your head. I could give you a few seconds, but I'm going to save you the headache and tell you that you cannot. But proving that you cannot is kind of hard, because you have to do an exhaustive check of every possible route. So what's the better way of doing it? The better way is to try and think of this in terms of graph theory. You have land masses and you have connections between land masses. And so instead we could draw a map of the city of Königsberg, their land masses, and their bridges. Here we show every connection possible between those land masses and the connections, the bridges between them. And you'll notice that between C and B there are 2 lines, and that's because there's 2 bridges, right? So are you going to go bridge A or bridge B? Same thing between B and A. Every place else has basically 1 bridge that they connect to, but that means that you have multiple bridges coming in. Bridges, by the way, are not directional. You can walk across a bridge in either direction, so we're not going to use arrows here. We're going to use an undirected map or graph. And so we've got the problem of the bridges of Königsberg. And so this problem created a famous mathematician by the name of Euler. I know you want to pronounce it Euler. I believe it's Euler. It's been a while since but I'm pretty sure. And so anyway, he didn't use graphs exactly. This is the problem that started graph theory. He is sort of the father of graph theory. His explanation had the same concepts that would eventually become graph theory, but he probably never drew it this way. He had a different way of showing those relationships. But again, it's about objects and their relationships and expressing those ideas mathematically. So using this, he said that really what mattered, the layout of the city doesn't matter. What matters is the relationships between the land masses. How many connections do they have to the other places? And here you can actually see the number of connections that each landmass has. C has 3, D has 3, A has 3, and B has 5. You notice those are all odd numbers. And so using these concepts, he was able to actually prove 2 things. 1, it is only possible, and I believe they call this an Euler circuit. Don't quote me on that. It's a famous thing in math, but it's called an Euler. You can only cross every bridge once and only once if only 2 of the vertices have an odd number of connections. And the reason for that is because then you have a starting place and an ending place, right? Like now you know where you have to start and you know where you have to end. So long as you have 2 that are odd and every other vertice is even, has an even number of connections, then you can cross every bridge once and only once. The other is if every vertice has an even number of connections. If you have at least 1 odd number, you have to have 2, and because you have to have a place to start and a place to end. And if they're all even, then you're perfectly fine. Those are the only possible times where you can cross every bridge once and only once. Clearly, that didn't work here. As a side note, I think I've linked a resource video. Turns out that, I guess during one of the world wars, some of the bridges got blown up, and it was then possible, but that's cheating. You don't get to use bombs to solve this problem. Anyway, so that is sort of the birth of graph theory. Let's talk about more terminology when it comes to graphs. We're going to start with these 2 graphs, which are actually the same graph. One is just the underlying undirected graph of the directed graph in G. So G has the directions. H just shows, is there a connection at all between these 2 nodes? But we're going to need both because the terminology will be a little bit different depending on if we're talking about an ordered or an unordered graph. So we're showing the same graph two different ways. One is degree. So degree is the number of times an edge touches a vertice or a node. So this is different, by the way, than the number of edges that touch it, or sorry, the number of edges that are touching it, because you can have loops. And so that's why you have that little loop there for X. So vertex X in graph H has a degree of 5, because it's 5 connections, right? It's got the connection to W, Y, Z, and then the connection to itself actually touches itself twice, right? You've got 1, 2, 3 plus 2 for the loop. Because you can either, well, this is undirected, but in directed you could leave and also come back through that connection. So it has a degree of 5. W has a degree of 2, right? Y has a degree of 2. V has a degree of 3. There are 3 connections going in and out of it. So those are the degrees of the vertexes. There's also 2 related notions for directed graphs. So for directed graphs, we would say in degree and out degree, meaning that we need to know specifically how many on-ramps are there and how many off-ramps are there. How many places can I leave a node and how many places can I arrive at a node from, or a vertex. So for here, A has a in degree of 1. Point A, there's only one way to get there, and that's from point D, right? The arrow's pointing in. It has an out degree of 2. There are 2 ways you can leave A. You can either go to B or E, right? But that's your possible connections. C, in this case, has an in degree of 2 and an out degree of 3. So remember that loop has 1 out and 1 in. So you can come in from either B or from C itself, in degree of 2. You can go out to D, to E, or back to C itself. So don't let the loops fool you. And by the way, loops would be possible, especially if you have something that's sort of like an idle process while you're waiting. But anyway. Paths. So a path can be defined as a sequence of alternating vertices and edges. So where do you start? What edge are you going to take? Because remember, right now we don't have our edges labeled, right? But you could actually label those edges because you might have more than one edge between 2 vertices. Going back to our medieval town example, there were some land masses that had 2 bridges. So you'd have to decide which bridge that you're going to take. So it's just a combination: vertice, edge, vertice, edge, vertice, edge, vertice, edge, right? That's it. So here we've got, I could draw a path from B to C, C to E, and then I'm sort of done. There are no out. Point E has an out degree of 0. I can't go anywhere from there, but that is at least a path. So you're defining a path through a graph. A circuit is any path that ends where it began. So can you get back to where you started? So for instance, there is a circuit from B to C to D to A back to B, right? That is a circuit. There is no circuit that includes E, because E is a dead end. I suppose it would also be a circuit to go from B to C to C to C to C to C to C to D to A to B, right? But I can't include E. We would say that an undirected graph, right, and this only applies to undirected graph, is connected if there is a path connecting any 2 vertices, meaning that regardless of direction, is there at least a connection between 2 points? And so we would say that this graph H is connected. It doesn't matter where you're starting from W, I can go from W to X to Z, I can go from W to V to Z, I can go from W to X to Y, to V, to Z, to X, to W. I can get anywhere, right? There's always a connection. If it's a directed graph, it's considered connected if the underlying undirected graph is connected, right? So Doesn't matter that, yes, I can't, if I get to E, I'm stuck. Doesn't matter, I can still get to E, right? That's all that matters. So if the underlying undirected graph is connected, then we say the directed graph is also connected. Now, the idea of graph theory is that we're going to try and use it to model real-world projects, problems, relationships, things, relationships between stuff, cats, dogs, whatever. And so we want to model these relationships in sort of a mathematical way. So here's the example from your book. A college registrar would like to schedule the following courses in as few time slots as possible. However, they know that there are classes that always have students in common. Computer science students, for instance, need to take physics, and physics students need to take computer science. There's going to be an overlap in those students between physics and chemistry, between calculus and chemistry, calculus and physics, calculus and computer science, calculus and everything. Yeah, everybody needs calculus, right? And so these are the pairs of classes, the disciplines that have students in common, where you wouldn't want to schedule them for the same time slot, because if you schedule them at the same time slot, then your students wouldn't be able to take both courses, right? So we want to make this, how many time slots do we need so that we can get all of these classes without having any of these relationships being conflicts? If you think about it right now, just off the top of your head, how many do you think you would need? Is it like 5, 8? Is it 2? Right? What's the number? So the way that we're going to solve this is by using graph theory. We're going to try and model this as a graph. And so that means we can show all the different disciplines, and then the relationships between those disciplines, where the relationship here means you have students in common, right? Students are going to need to take both of these disciplines if they're in one or the other discipline. So this is the relationship that we see listed in text over here. Calculus is in the center because it has relationships with both chemistry, physics, computer science, discrete mathematics, and biology, right? We would say that calculus has a degree of 5, right? It's 5 different connections to other things. In fact, the only thing calculus doesn't connect with is psychology, which, by the way, hey, that's probably 2 that we can schedule for the same time slot, but we're not there yet. So then there's also relationships between physics and computer science, and physics and chemistry. We would say that physics has a degree of 3. In fact, you actually kind of see that most of these actually have degrees of 3, except for calculus, which has 5, and psych, which only has 2. But that is a good representation of a model of our problem. Now that we've got that, let's go ahead and try and use it to solve the problem. So we're going to start out with calculus because it has the highest degree and the highest number of conflicts. So we'll put that as our first time slot. Now these time slots don't actually have to be first, right? Again, they just have to be different time slots. So we're not saying, when I say the first time slot, I'm not saying that it's the earliest in the day. We don't need to worry about that. That's a level of complexity for whenever. We're just saying that the first time slot that we're looking at, regardless of where we put it, that time slot is going to have calculus in it. So then, once we know that we have calculus in time slot A, we just have to pick a discipline that can't be in the same time slot as A. Let's choose computer science, right? So computer science, because it conflicts with calculus, has to be in B, right? If we have that, then we say, well, is there any discipline that can't be in calculus and also can't be in computer science or connected to computer science? There's actually a couple. Discrete math would work, but also physics. So let's put physics in time slot C, right? Because physics can't compete with either calculus or computer science. So now, at this point, we have 3 time slots. The question is, do we need any more than 3 time slots? Let's see if we can start fixing in other stuff. Like chemistry, for instance, has no conflict with computer science. So chemistry can go into time slot B. Done. If we look at the next one, we can see that discrete math doesn't conflict with physics. So discrete math can go into time slot C. Bio also doesn't conflict with computer science or with chemistry, so it can go into time slot B, right? Psych doesn't conflict with calculus, so it can go into time slot A. and we're done. We were able to get all of the classes, all the different disciplines put into time slots, and we only needed 3 time slots to do it, to handle all of those different relationships. So there we go. We've been able to solve some conflict using a model that we created with graph theory. Now, by the way, that graph could then be enhanced with coloring. So coloring is one of the ways in which you can add additional information to a graph, and we'll have a few other ways of doing it too. The idea being that now we have this new thing we can represent. Not only do these disciplines have students in common, but also do these disciplines, like what time slot do these disciplines fall into? They fall in time slots A, B, and C. Well, we could just assign those to colors, right? So psychology and calculus, time slot A will make red. Chemistry, computer science, and biology will be yellow, and physics and discrete mathematics will be green. So now we can actually, just looking at our graph, not only look at what the objects are, or in this case the disciplines, what the relationships between those objects are, do they have students in common, but we can also look at what time slot are they in, based on the color of the actual node or vertice. So that's a coloring problem. There's kind of something that's related here. So planar just means that if you actually were to write this on a piece of paper, right? Something that is on a one single plane, and you can do it without any edges crossing the other. All right, so there's no overlap of stuff. Then we would say that it's a planar graph, right? It can fit on a plane flat without any overlap. Because any overlap would sort of imply that you're not on a single plane anymore. You're sort of on 2 planes. One has to go over or under the other. So if that's the case, there's this thing called the 4-color theorem. The 4-color theorem states that for any planar graph, you can color it with at most 4 colors without having to worry about any of the colors overlapping, right? You can see that chemistry is not connected to any other yellow dots, calculus is not connected to any other red dots, and physics is not connected to any other green dots. In other words, we've kept them all separate, which was our whole goal. You can color it if the graph is planar. It doesn't matter how many of these additional relationships and disciplines we add, so long as you can represent it in a planar way without having to overlap any of the edges, you're only going to need 4 colors, which in this case represents time slots. So with 4 time slots, you can do a whole bunch more, unless you get overlap. This also, by the way, your book happens to mention, means that cartographers only need 4 colors of ink, because for any map, unless your borders were to somehow like overlap each other, which they don't, well, actually, they probably do in the real world somewhere. I have to imagine there's 2 different countries that have, I think it's here, I think it's here. But anyway, for us in the United States, right, you can draw the map of the United States with 4 colors, and none of them will have a neighboring state that has the same color. It's possible to do that because of the 4-color theorem. The map of the United States is a planar graph, planar map, right? None of the borders overlap, so we can do it with just 4 colors. And I know what you're thinking. You're looking at New Mexico and Utah over there. The 4 corners, technically, they're not next to each other. They're just the corners are kind of touching a little bit. But that was a good thought. Anyway, moving on. Let's get even more complex with these graphs. We can turn them into networks. So networks are basically a graph where you have some sort of a weight or numerical value or something that you're sort of using to represent whatever it's going to be. It could be time, for instance, the latency between nodes on a network. How many milliseconds is the ping between 2 particular nodes. That could help me define the fastest route, maybe between one node and another. If you ever taken networking, this will make total sense to you. In fact, you've probably seen a graph that looks a lot like this one. This one, however, is actually cities in the state of California with the number of miles between the different cities. And so we can take the information that we have there in the table with the different miles, and let's assume that these are the only routes available, the only freeways available. With that being the case, we could actually determine like what's the fastest route between two cities. Now, for instance, if I was going to go from San Diego to Fresno, if you're looking at this graph, you're going to think, oh, well, the easiest way is to go from San Diego to Barstow to Fresno. Because the way the graph is drawn, it kind of looks like that's the shortest route. But you know that it's not because you live in the real world and you've probably driven to San Diego at some point in your life. You do not drive through Barstow. 175 miles plus 245 miles is longer than the 125 miles to get to LA and the 220 miles to get to Fresno. That's the fastest route, San Diego to LA to Fresno, and you kind of already knew that from the real world, but that's the whole point. Remember that these, like, if you look at Eureka, the distance of the actual line in the graph between Eureka and Fresno and Eureka and Los Angeles is the same. And you know that the number of miles is not. 450 miles to Fresno, 645 to get to LA, right? Those have dramatically different weights, right? They have dramatically different values, even though they're drawn the same. So just know that when you're looking at a network, it may actually be that in the actual drawing, you might actually backtrack, go way out of your way to get to someplace just because, well, actually, the latency on the nodes in the server, kind of, this is the fastest way to get there. It's just the way that we drew the graph, because all we care about are what are the objects, what's the relationship between the objects, what are the nodes on the network, and what is the latency speed between those nodes. We don't actually care about where they land on the page. This is, by the way, not a planar graph. You can see some of those lines overlap. Anyway. And this gets to our last concept, binary search trees. If you've already taken 41, you've probably already played with some binary search trees. But the idea is that a binary search tree is actually a type of graph, right? It's subject to graph theory. So let's take this example. You have a custom dictionary and a spell checker, right? Because like there are words that I use that, other people wouldn't. I don't want you to correct me when I use slang or whatever. And so your custom dictionary will learn new words as you type them in, words that aren't in the dictionary to begin with. The correct spelling of people's names in your life, for instance. And so here we're going to add words one at a time, no particular order, but then we're going to have to find a way to organize them so that we can find them easily when we're searching for them. One of the ways we can do that is with binary search tree. And so here we've got a custom setup. We've got some weird words, macchiato, posit, which is actually a math term, fat, the colloquial phrase for something that's good if you're, I guess, my age, complexify, jazzed, yada, yada. We've got some words here that we're going to put into it. So what's a way to efficiently deal with this? The binary search tree. It's a graph structure that has a couple different rules to it. It always starts with a root node at the top of the tree. That's probably just the first word that goes in, although eventually you might want to balance the binary search tree, which is a different topic, but we'll get to that later. And so the idea is that for every node in a binary search tree, including the root node, you can have two children, right? A left and a right. Now, depending on how you draw this, whatever, but picture node, left and right. The left node is always going to be less than, and the right node is always going to be more than, whatever the node in the middle is. All right, so the idea is that if we're going to do things alphabetically, right, I know that whatever the word X is, the word to the left is going to be earlier alphabetical order than X, and whatever's to the right is going to be after X in alphabetical order. So the correct order in your alphabet is going to be LXR. And that's going to be true whether or not I'm doing something alphabetically, which is the case for our dictionary. We're going to use alphabetical, but it could be numerical. It could be representing latency speeds. It could be represent whatever it's going to represent. It's going to represent some sort of order, right? And so the order should always go LXR. If it's alphabetical, it's apples, bananas, carrots, right? Bananas would be X, L would be apples, R would be carrots, right? That's the order. So if we were to start putting these words into our custom dictionary, we would start with macchiato, and that becomes the root of the tree. After macchiato, we're going to add posit, which I believe stands for partially ordered set. I believe you pronounce it posit, not posit, but I've only ever seen that word like in a book, so I don't actually know how you pronounce it. Regardless, posit, it's short for partially ordered set, and it comes after macchiato, right? Because P comes after M. The next word is going to be fat. Well, fat comes after macchiato, so we're going to go to the right. Then we find the word posit. Is it before or after posit? Well, it's before posit, so we go to the left, and that's fat. We're going to keep doing that with every single word until we eventually end up with this tree that contains all the words in the general order. Now, by the way, turns out we ended up with like a perfectly balanced binary search tree. There is no guarantee you're going to get that, right? If the fourth word had been after macchiato but before fat, right, we would have gone macchiato, posit, fat, and then back down to the left. And in fact, if every single word that you get comes earlier in the dictionary, then you're always going to get just left children, right, all the way down, which means that any search on this binary search tree is actually going to be a linear search, right? You're not going to get any time savings. The more balanced your binary search tree, the more efficient that search tree is going to be, which means that at some point you're going to want to optimize and possibly refigure the tree to balance it out. But that being said, let's look at why it's faster. How do you actually find a word in a binary search tree? So I want to try and find a new word. The word that I'm going to try and find is weeb. It's just a slang term for somebody who really loves anime, like really, really loves anime and probably dresses like an anime character from time to time, cosplays, does all that sort of stuff. Somebody's really, really into it. Weeb. So that word starts with a W. So I'm going to go to macchiato. And basically, I'm going to follow the exact same rules that I would use if I'm going to put the word into the tree, right? Go to macchiato. Is it before or after? Is it equal to macchiato? No. Is it before or after? It's after. Okay, so then I go to posit. Is it posit? No, it's not. So is it before or after posit? Well, it would be after. So then I find sheafify, which I believe, I can't remember. It's something about graphs. You have sheaves and pre-sheaves. It's not graphs. Sorry, it's a different type of math. But anyway, regardless, sheafify, right? That is, well, is it weeb? No, it's not. Is it before or after? Well, weeb would come after. Oh, well, if I were putting weeb into it, I would put it to the right child. But I'm just looking to see if it's in the dictionary, and there is no right child. So since there is no right child, I know that weeb is not in the dictionary. If I were just trying to find the word jazzed, I would look at macchiato. Is it macchiato? Nope. Is it before or after? It's before, so it's complexify. Complexify, is that before, or is it equal to jazzed? Nope. Is it before or after? Well, jazzed would be after, so I go check it. Find jazzed. Is jazzed equal to jazzed? Yes, it is. Okay, so this word is in the dictionary. So binary search trees are nice. I can do in 3 checks, right? 3 comparisons. I can find here all 7 words. Now, by the way, that is really unimpressive. If you think about it, a linear search of 7 words on average can be done in 3.5 comparisons, right? So then I'm only losing a half a comparison. But the thing is, right, as the data sets get larger, that gets better because every new layer of your binary search tree, every new layer is going to have twice as many values, which means that if you had a balanced binary search tree with 255 nodes, right, 255 possible words, it would require at most 8 comparisons to search it completely. You might get it in less than 8, right? So we would say the average number of comparisons, actually no, in a binary search tree it's not exactly half because it's not linear, because you have heavier weights towards the end, but it would be something like 5 or 6 or something like that, right? That would be your average number of comparisons. Much, much better, right? And by the way, if you were to look at the very bottom, those tiny little children at the bottom of the binary search tree, there's 128 of those, which means that the next thing, if we were to go on or at most 9 comparisons, we would be adding another 256 nodes, almost doubling the amount of nodes that we have just with one more comparison. And if we wanted to get double that, we would only take 10 comparisons, right? And all of a sudden, we're now up to 1,000 something nodes with just 10 comparisons. Like as you get to millions of comparisons, or sorry, millions of nodes, you're going to have a lot of dramatic savings in terms of just search efficiency. So that's why we use binary search trees, or why, well, we do more stuff than that now. We do a lot of indexing, but regardless, yeah, binary search trees. Maybe I'll throw in a resource video about index searching. Might be good. Not related to this class, but it's a resource. It's extra behind the scenes stuff. And so that is it for the graphs chapter. We will start talking about other relationships next week. But until then, if you have any questions, send me a message in Canvas, and I will see you online.